Welcome to the Explainer. Today, we are pulling back the curtain on the invisible architecture that runs pretty much our entire digital lives. We're talking about the mathematics of trust. The cryptographic tools that make secure banking, private messaging, and even cryptocurrencies possible. So, let's get started. It all really boils down to this one fundamental question. Think about it. On the internet, anything can be copied, perfectly and endlessly. So, in a world like that, how do we prove something is the one true original? How do we keep a conversation private when anyone could be listening? How do we know who we're really talking to? Well, the answer is this brilliant set of tools built on pure mathematics. So, here's how we're going to tackle this. We're going to build our understanding from the ground up. First, we'll figure out how to keep a secret. Then, we'll see how to make sure data hasn't been changed. After that, how to prove who actually sent the data. And finally, we'll put all those pieces together to see how they create something as revolutionary as a blockchain. Okay, so our first challenge is the most basic one of all, privacy. If you want to send a secret message to a friend, how do you stop someone else from eavesdropping? This is the classic problem of encryption. So there are two classic ways to solve this. On the left, you've got symmetric cryptography. It's kind of like having a single physical key for a lockbox. Super fast and efficient, but now you have a new problem. How do you get a copy of that key to your friends securely? If someone intercepts the key, your secret is blown. But the solution on the right, asymmetric cryptography, is just brilliant. Everyone gets two keys. A public key they can share with the entire world, think of it like an open padlock, and a private key they keep totally secret. Now anyone can use your public key to lock a message, but only you can unlock it with your private key. The key sharing problem? It's solved. And that brings us to a really modern and powerful version of this called elliptic curve cryptography, or ECC for short. Now, instead of just using giant prime numbers, it uses the really unique mathematical properties of points on a curve. It sounds complex, I know, but the result is a massive, massive leap forward in efficiency. And the practical benefit here is just enormous. With ECC, you get the same or even better security, but with much, much smaller keys. This means everything is faster. It requires less computing power, which is absolutely essential for the devices we use every single day, like our smartphones and all those smart gadgets in our homes. And this right here, this is the payoff. A key that's just 256 bits long provides the exact same level of security as a massive 3072-bit key from an older system. That is a huge improvement in efficiency, and it's precisely why ECC is at the heart of so much of our modern technology. Okay, so we've made our message private. Awesome. But what if someone intercepts it and just changes it before it gets to its destination? How do we know the data we received is the exact same data that was sent? This is the problem of integrity. The solution is an amazing tool called hashing. The best way to think of it is like creating a unique, one-of-a-kind digital fingerprint for any piece of data. It doesn't matter if it's a single word or an entire movie, a hashing algorithm will crunch it down into a short, fixed-length string of characters. And the crucial part is, it's a one-way street. You can't ever get the original data back from its fingerprint. But, not all fingerprints are created equal. A secure cryptographic hash needs these very specific properties. For example, collision resistance means it's practically impossible to find two different files, say two different legal contracts, that somehow produce the exact same fingerprint. And that is vital for trust. But the most dramatic property, the one that's really cool, is the last one, the avalanche effect. This is wild. If you take a file and change just a single comma or one single pixel in a picture, the resulting hash won't be just a little bit different. It will be completely and unrecognizably transformed. This makes any tampering, no matter how tiny, stick out like a sore thumb. Great. So our message is now private, and we know it hasn't been tampered with. But there's one more piece to this puzzle: authenticity. How can you be absolutely certain the message came from your friend and not from some imposter pretending to be them? This is where we combine our tools to create what's called a digital signature, and it's a really brilliant process. So first, the sender takes the digital fingerprint, the hash, of their message. Then they do something really clever. They encrypt that fingerprint, but they use their own private key to do it. This encrypted hash, that's the signature. So how do you verify it? When the receiver gets the message, they do two things. First, they calculate their own hash of the message they just received. Second, they take the sender's signature and decrypt it using the sender's public key, which everyone has access to. And here's the magic moment.
If the decrypted hash from the signature is a perfect match for the hash they just calculated themselves, it's valid. They have just proven two things beyond a shadow of a doubt. One, the message wasn't altered, and two, it could only have been signed by the one person in the world with the corresponding private key.
So let's recap. We've got privacy, we've got integrity, and we've got authenticity. We have all of the building blocks we need. Now let's see what happens when we put them all together to create something truly groundbreaking, like a blockchain. So the core idea of a blockchain is actually pretty simple, but it's incredibly powerful. Each block of data, which might contain transactions or other info, also contains one very special piece of data, the hash, that digital fingerprint of the block that came directly before it.
And this is what makes the whole chain so secure. That link creates a cryptographic chain. If some bad actor tries to go back and alter the data in, say, block number 10, the hash of that block is going to completely change. Well, that means the hash stored inside block 11 is now wrong, which in turn changes block 11's hash, which then breaks block 12, and so on and so on. The entire chain, from the point of the fraud forward, just falls apart like a row of dominoes, making the tampering immediately obvious to absolutely everyone.
But wait, what about all the data inside each block? A block may contain thousands and thousands of transactions. Hashing them all one by one would be pretty inefficient. The elegant solution to this is called a Merkle tree. It's a structure that basically uses hashing over and over again until you're left with one single hash that represents everything inside the block.
Here's how it works, from the bottom up. You start by hashing every single transaction individually. Those are the leaves of our tree. Then, you take pairs of those hashes, you combine them, and you hash them together to create a new level of branches. You just keep repeating this process, moving up the tree, until you're left with one final hash at the very top. That is the Merkle rote, a single, elegant fingerprint that summarizes and secures every single transaction below it.
And there you have it. Starting from just a simple need for privacy, we've used these fundamental tools, encryption, hashing, and digital signatures to build these incredibly complex, secure, and trustworthy systems in a digital world that by default has none of those things. We've literally constructed trust purely out of mathematics. So the only real question left is, what's the next big problem we can solve with it?